Right. I propose we start. Welcome, everyone. Welcome to this monthly webinar about the value of water in Canada. I'm very happy to see you again. Before I introduce the speaker of today, I would like to acknowledge that I'm participating today from traditional territories of the First People. I participate from land that is part of the traditional territory of the Neutro, Anishinaabe, and Haudenosaunee people. Our main campus at the University of Waterloo is situated on the Haldimand Tract, the land granted to the Six Nations that includes 6 miles on each side of the Grand River, as you can see in this map. The University of Waterloo and its centers and institutes like the Water Institute that I represent here today are committed to raise awareness and contribute to Canada's Truth and Reconciliation Commission's calls for action. And I encourage you to take a moment to recognize the traditional land where you are. Before I introduce the speaker, if you have any questions to the speaker today, use the Q&A box, please, not the chat, but the Q&A box, and then we'll get to your questions after the presentation. Only use the chat box for technical issues, and then my colleague Julie Grant will try to help you with that. So let me move to the introduction to the speaker of today. I'm very happy to have Professor Duncan Knowler here with us, professor at Simon Fraser University in Resource and Environmental Management. He's a very well-known Canadian environmental economist with an extensive experience in the environment and development field. His research interests include economics of natural resource management in developing countries, valuation of environmental resources, and applied bioeconomic modeling. Prior to joining SFU, he was employed at the FAO in Rome, where he was involved in natural resource management related project work in developing countries in cooperation with host governments and financing institutions. His research has included studies of nutrient enrichment and commercial fisheries in the Black Sea in Europe, the economics of invasive species, the prospects of community wildlife management in Nepal and Mexico, the sustainability of shrimp mangrove systems in India, and valuing the preservation of fish spawning in spotted oil habitat in Western Canada. So a very rich background and experience. He's been involved in a number of overseas research and project preparation studies, including biodiversity-related work for the World Bank in Nepal, tribal development in India, and integrated pest management in Indonesia. He has prepared studies for the Convention to Combat Desertification, the Ramsar Convention on Wetlands, and several studies on sustainable agriculture for the FAO while he was at the FAO, but also afterwards, including a background paper for the FAO's World Food Summit 5-year review. And his talk today is about valuing the benefits from improving management of freshwater fish habitat in British Columbia. So Duncan, we're very happy to have you with us here today, and I'm happy to hand over the floor to you.
Great, thanks a lot, Roy. Appreciate that. I'm really happy to be here and to sort of reflect on some of the work I've done over time, and I'll get started. So I want to share the screen here, so I'm going to just put that up. Are you seeing the right screen there, Roy?
Yes.
Yeah, okay, good. So the title of the talk is Valuing the Benefits from Improving Management of Freshwater Fish Habitat. I'll say just salmon, we're only going to deal with salmon. Reflections from 2 case studies in the Pacific Northwest. And I'll include the Northwest of the US, in particular Washington State, as well as BC. The 2 studies that I'm going to talk about follow a common thread over time in terms of my research approach. The first study was done many years ago, now almost 20 years ago, but was followed by another study more recently, carried out primarily by a PhD student for his thesis work, but we published together in the journal Ecosystem Services. So let me move to my second slide here. So basically, these case studies describe applied bioeconomic and valuation modeling in two river basins. One is the South Thompson River Basin in BC. That's the older study. And the second one is the Columbia River, familiar to everyone, in the main stem running through Washington State. The papers basically follow, as I say, a sort of common methodology, although they're separated in time. They both represent bioeconomic modeling to estimate net economic benefits that are consistent with economic welfare theory. So the point here is that we formulate these models so that we capture the correct measure of value, which in this case is economic rent, attributable to commercial salmon fisheries in these river basins. In each case, we estimate a stock recruitment relationship at the basin-wide aggregate level. And I'll explain why we do that rather than just in an individual stream or two. We start with that, but we need to aggregate it up to the basin to account for how the fishery is undertaken at that scale. I'll explain more about that in a minute. We also, the key piece here is that we incorporate habitat quality into the stock recruitment relationship, and that is how we effectively capture the notion of valuation of habitat change, because we can trace that through when there is a change in habitat quality, ultimately to the impact that has on the net benefits or net economic benefits attributable to the fishery. And that is our measure of benefit. So in effect, this is a form of production function valuation modeling. It really has nothing to do with stated preference approaches, which you may be familiar with, surveys, willingness to pay questions, things. No, this is purely rooted in production economics and the idea of the environment as an input to production, in this case, the production of commercial salmon. So basically, they involve developing the relationship between the environment and the productivity of the fishery through a number of habitat quality scenarios. These are combined with a biological model for the recruitment in the fishery to determine how changes in habitat quality or comparisons of different scenarios result in different levels of fishery productivity. And then ultimately we pass it through an economic model, which then turns those results into economic values. So the first study is in the South Thompson River. This is the Adams River sockeye run, a very famous, most famous in the world, I think, sockeye run, which is part of the Thompson River Basin. And this paper was published in the Journal of Environmental Management some years ago. Okay, so a little bit of background. The South Thompson River Basin is shown here with the dotted circle around it out in sort of eastern BC. It's an important spawning area for various species of salmon. We're going to focus on coho salmon, which use this area extensively for spawning. Now, these fish spend about a year or so in the river basin and then eventually find their way out to the ocean through the Fraser River, spend a couple years at sea, and then come back and pass up the Fraser River and into the South Thompson River Basin to spawn. So that's a 3-year life cycle. The commercial fishery is largely carried out in the Strait of Georgia. There's recreation fisheries, indigenous fisheries, and such, all mostly carried out down in the lower parts of the river and in the Strait of Georgia. So there's a disconnect then between the area of reproduction and spawning and the area of commercial production and catch. Now, in the South Thompson River, we had data for 16 streams of various sorts. We had data on habitat quality as well as reproductive success in terms of spawning and recruitment and such. Spawning, anyways, success. So we were able to relate these to each other, and that's the basis for the modeling. Okay, so the research questions: how do changes in land use, within this case the South Thompson River, affect the productivity of coho salmon populations, and what are the resulting economic impacts on coho salmon fisheries in the Strait of Georgia, BC? Okay, so this is what we're trying to look at. We'll focus on just the coho. Okay. All right, so now I'm going to hit you with a little bit of math here, just to show you the basic constituents of the valuation model. So to start with, we have a statement for the net benefits from the commercial fishery. You can see this equation number one. These are essentially calculating, this is essentially calculating economic rent from the commercial fishery. The variables X and H are the key variables that determine the outputs, and the various variables are defined here. You can see that. Now, this economic expression is subject to a biological constraint. You can't just harvest as many fish as you want without consequences. And the biological constraint basically constrains us to recognize the relationship, or the recruitment relationship in the fishery, which is shown as number 2 here. A couple things I want to point out here. First of all, you'll notice the little lags in the subscripts here. There's a difference of 3 years between the X on the left-hand side of the equation, T plus 1, and the X and the H inside the brackets on the right-hand side. And that constitutes the 3 years in the life cycle of coho between reproduction, spawning, and eventual recruitment to the exploitable population, which is accessed by the commercial fishery. So we have to account for this gap in time. The other thing I want to point out is the Q on the right-hand side. That is our habitat quality indicator, which we'll develop further in the rest of this. We put a bar across to signify that it's fixed for the purposes of our modeling. But this is going to tell us, essentially, this is going to allow us to assess how changes in environmental quality can be traced through ultimately to changes in harvest and exploitable populations, and then ultimately to differences in economic rent under different scenarios for environmental quality. Okay, so all of this results in a constrained optimization problem where our objective function is shown at the top. We want to maximize the economic rent, the net benefits from the commercial fishery, subject to the constraint imposed by the biological relationship seen here in the essentially the recruitment function. Now, this is all subject to discounting because we're looking at a long time frame. We show infinity here as the length of the time frame up in the top. We have a discount factor rho with delta shown as the discount rate. So we're taking account of the time value of money by discounting future years back to the present. Okay, so the valuation side of this, or valuing changes in habitat, can be done 2 ways. One is to look at what happens if there's a tiny change in the level of habitat quality. How do we account for that in terms of ultimately changes in economic values? And that's what this expression 4 is. For those who are math oriented, this is an example of applying the envelope theorem in calculus. And the expression on the right-hand side basically tells us if we change Q by a little bit, keeping everything else the same, how much does the economic rent change? So it might be a 1% change in Q leads to such and such a change in economic rent. That's one way of looking at it. The other way is from the point of view of a non-marginal change, where we're actually comparing completely different scenarios where the habitat quality could be quite different, in which case we're no longer just looking at a tiny change in Q, but rather a bigger change, say from QA, which is pristine conditions, to QB, which is environmental conditions under just more disturbed circumstances. That expression is shown below, and we use that to determine the changes in economic values associated with changes in habitat quality in the rest of the discussion. Some some of the functions and relationships that we use. The one at the top is the actual recruitment function, telling us how many fish are recruited to the exploitable population each time period. This is actually, it looks complicated. It's, for those who are familiar, it's what's called a Beverton-Holt recruitment function. It has several parameters here. A, B are production parameters in the Beverton-Holt recruitment function. The M on the top is the adult survival after the period in the marine environment. And the rest are should be familiar. Q, X, H are all familiar at this point. The benefits, because salmon is a internationally traded commodity, we assume its price is fixed internationally, and therefore we take a simple statement for the economic the revenues from the harvest, just P times the harvest, price is fixed. And then we have a catch function or effort function, which shows E as the level of effort, fishing effort measured in days. And we build this basically as a discrete time model, because we're looking at effort in each time period rather than in a continuous sense. So all of these together are formulated into our constrained optimization problem. Okay, so I want to move on to the environmental side of this. How do we actually incorporate environmental quality and habitat conditions, and such that we can look at how changes in those conditions feed through to the value of the fishery? So we have these 16 South Thompson streams, and we have observations on various aspects of environmental quality in each of these sort of stream basins, if you will. Things such as the area of roads or the length of roads, the amount of logging or agriculture, all of these things. There's 10 different indicators that are observed for each of the 16 streams. Now, by looking at each of these indicators in terms of either high impact or low impact, just a simple binary kind of indicator, we count up the number of high impacts across all those indicators, and then with that construct the habitat concerns index. And I should mention that although there's 10 indicators, several of them have a number of sub-indicators, so that we could actually have as many as quite a few different indicators involved. By simply counting up how many high impact scores we receive, we create this habitat concerns index. And so the value of that index runs from 0 to 20. You can see the frequency distribution of the 16 streams. There are 4 of them fall between 6 and 9 on the habitat concerns index. The nice thing here is there's a reasonable dispersion. So we have a range of different habitat conditions. The ones on the far right hand are more seriously impacted, whereas the ones on the far left hand have relatively little impact. Okay, so the trick then is to relate the habitat conditions reflected in that index to actual fish productivity. And here we see a plot of the habitat concerns index across the top to an indicator of recruitment success or changes in recruitment success over time. Notice they're all negative because recruitment has been declining in these streams over time, but in some cases worse than others. So we fit a line to this data to give us a relationship between the Habitat Concerns Index and success with spawning and eventual recruitment. And you can see that's it's a downward sloping relationship, as you'd expect to get. The more the habitat concerns, the lower, the worse is the trend in recruitment. Okay, so in order to translate this into parameters we can use in our constrained optimization model, we carry out a simulation, essentially a calibration, using the information in that last graph to calibrate for the parameters in the recruitment function, particularly the productivity parameters in the recruitment function, remember the A and B, as well as to be able to express the habitat conditions in a form that's compatible with the way we've modeled it. And so we use this is a looping simulation model that helped us to allowed us to calibrate for those parameters that we need in the model. Okay, so what we get out of that on the habitat quality side is a habitat quality factor, which is on the right-hand side, which is basically an index between 0 and 1. And you can see from the note at the bottom, it represents the proportion of smolts that are produced in relation to pristine conditions. Now, that was derived from the Habitat Concerns Index. Remember, that went from 0 all the way up to 20 in the worst case stream. And you can see, for example, the yellow highlight at 10 is the average condition across the 16 streams. So the 0.47 in the quality factor basically is says that roughly you're only getting roughly half the number of smolts produced in those streams as you would under pristine conditions. So we can use this Q as a kind of scaling factor on our recruitment function in order to observe how recruitment and fisheries productivity changes as a result of changes in the underlying habitat conditions. So that gives us what we need. Okay, so the scenarios we look at, there's 4 scenarios. Because the coho in the South Thompson mix with other stocks of coho from other river basins, ultimately in the Strait of Georgia where the commercial fishery is carried out, we have to model the whole system at that scale. We can't separate out coho and only catch them or adjust the catch on the coho that are coming from the South Thompson. So we need to account for the entire basin feeding into the Strait of Georgia, of which the South Thompson area is just a smaller sub-basin. So what we do then is we consider 2 cases within the South Thompson itself. One is where conditions are degraded from pristine conditions, where Q is equal to 1, in other words, pristine habitat quality, down to its current average condition, which is a Q equal to 0.47, or about 47% of the productivity under pristine. And we also look at a case where we allow it to degrade all the way to 0. So what if the entire 16 streams was removed from coho, the coho population altogether? What would be the impact of that? But then we have to make assumptions about what's going on also in the rest of the Strait of Georgia basin, because we're modeling the population at that scale. So we have the South Thompson we account for in terms of habitat quality, but also the rest of the basin. And we assume either it's pristine, where Q is equal to 1, or it's roughly the same average habitat condition as the South Thompson. So we set Q equal to 0.47. This mixing and matching within South Thompson and the rest of the Strait of Georgia gives us 4 different scenarios. And I'll show you the results here then. A lot of numbers here in this table, but don't worry about it. We're just going to focus on a few. We have 2 scenarios, A and B here. Both of them assume that the rest of the Strait of Georgia basin is in pristine condition. So we're only adjusting the quality within the South Thompson basin. The rest is assumed to be pristine. Not realistic, but just a useful reference, set of reference scenarios. In the South Thompson scenario A, we assume it's been degraded from pristine conditions, which is the first column, down to 0.47, or 47% of its productivity. And then the second, scenario B, is all the way to 0. So it's completely removed from the entire basin, Strait of Georgia basin. So when we weight that into the overall Q for the entire basin, in scenario A, it only falls a little bit from 1 down to 0.9878. But that's incorporating the decline in only the South Thompson basin. Similarly, in scenario B, it's more of a loss because we lose the entire South Thompson. That declines to a value for Q of 9.977. Okay, you can see some other numbers here. The number of fish recruiting is around 1 million. Though that changes under the pristine condition, and that changes under each of our scenarios. And you can see catch numbers for the optimal production level, fishing effort, and the rent that's produced, which is in net present value terms in the order of 64 million in the pristine state, dropping closer to 60 million in the other scenarios. Now, what's interesting is the numbers at the very bottom here, which are expressed on a per unit basis. The value of the habitat loss for the 16 streams is shown. They're carried down from the line above. But what's interesting is the amount of habitat loss per hectare of catchment area. And that's equal to about $2.63 in the first scenario, rising to almost $5 in the second scenario, where the entire South Thompson 16 streams are lost. We can also measure this in terms of per kilometer of water course in these 16 streams. And that's running from around $3,700 per kilometer lost under the first scenario to $7,000 in the second scenario, with the entire South Thompson loss. So fairly substantial numbers. These are present value numbers, by the way, at 5% discount rate. Okay, the second set of scenarios, scenarios C and D, assume that the rest of the Strait of Georgia, rather than remaining pristine while we allow the South Thompson to degrade either to 0.47 or to 0, we assume the rest of the Strait of Georgia is at the same average condition, habitat condition as the South Thompson. So we set that at 0.47. So much poorer habitat conditions in the rest of the basin. Of course, that then impacts on the commercial fisheries in the Strait of Georgia because the productivity of the fishery is lower overall. So in that context, we can see that the values down below are quite a bit lower, only about $1 per hectare for scenario C. And with the entire loss of the South Thompson in scenario D, it rises to about $1.70. And the values per kilometer are only, from $1,300 to about $2,300, $2,400 per kilometer. So you can see here that the condition of the rest of the Strait of Georgia basin outside of the South Thompson has quite a significant, dramatic effect even on the values associated with losses in the South Thompson's 16 case study streams. So an interesting observation there. Okay, so just to conclude this study, couple of observations. One of the things here is, in order to model this, we model it on the assumption that we can optimize the economic returns from the fishery, which means we can set the fishing effort at exactly the optimal level to maximize the amount of economic rent. What that means is, unlike historical conditions, where a lot of inefficiency might be built in because there's too much fishing effort chasing too few fish or whatever the case, in which case the values associated with habitat change would be much lower, we're able to focus in on just the values associated with habitat change. We considered the changes in the South Thompson separate from changes in the rest of the basin, and we just spoke about the impact of that. And we find changes in welfare, losses from the degradation of habitat quality in the range of $1 to $5 per hectare of drainage basin, or about $1,300 to $7,000 per kilometer spawning length. And I could also add that we carried out a sensitivity analysis, and the values were pretty robust, despite varying some of the key parameters. Okay, so I'll stop with that study, and I'm going to move on to the second one, which is in the Columbia River Basin in Washington State, published in Ecosystem Services Journal in 2017. So we're jumping ahead quite a number of years here, and while the modeling is more sophisticated, the simulation modeling is more sophisticated, the actual approach to habitat quality and incorporating habitat quality is quite similar. It uses the same basic ideas. Okay, so this is the Columbia River Basin. The yellow highlighted length of the Columbia River is the main stem inside the US from the Canadian border all the way to the ocean. The dolls shown down at the bottom is where most of the stream flow measures are taken. So we'll just identify that because we'll be using stream flow measures. The research questions in this study are somewhat similar, except we're going to focus on river management, flow management, which is primarily intended or focused on hydropower production, but has consequences for salmon conservation. So we want to look at how changes in that flow management, emphasizing more or less on hydropower versus salmon conservation, what the impact is on salmon populations, and then tracing that through, similarly to the first study, how that affects economic welfare. And although we'll focus on the commercial fishery, the study also accounts for subsistence fishing by indigenous people, recreational fishing, and we also include benefits from nutrient cycling, fish-related nutrient cycling. Okay, so modeling considerations, basically we focus on flow here rather than land use in the riparian areas around the water courses. We modeled flow and looked at how, under various circumstances of regulated flows, how these deviate from what would be a pristine, unregulated flow. So we maintain that idea of using a pristine, unregulated, unaffected system as our benchmark or reference point. We used the flow information and the differences between regulated flows and the pristine, unregulated flow to create a habitat quality index. So similar in concept to the first study. We use this HQI to estimate egg to spawner survival, which then feeds into recruitment relationship, and then model this under several different flow scenarios. For the modeling, in contrast to the first study where we look at optimizing the management of the fishery, we assume here a historical level of constant escapement every year of about 780,000 fish. So that's, you're always allowing 780,000 fish through to the spawning grounds. Anything that's left over after that is what's available to the various fisheries. We allocated whatever was left over for the fisheries to the commercial, recreation, and tribal fisheries using historical shares. Then we use these catches and economic data for each of these fisheries to determine what the economic benefits were under that particular flow scenario. Okay, a couple more equations similar to, in some respects, to our first modeling. The first one is our net economic benefits, again, simply revenues minus costs in the fishery. We'll focus mostly on the commercial fishery, but we'll account for the other ones later on. Recruitment, again, makes use of a Beaverton-Holt recruitment function with those A and B parameters. You can see those kind of hidden in there. We also allow for the lags, depending on which species we're talking about. The life cycle takes more or fewer years. A key point we want to make here is in the numerator on the right-hand side, you'll see in the first brackets a small s plus q. The s is the survival rate of eggs in terms of ultimately becoming spawners returning to the river. That's the egg to spawner survival rate, which is a measure of performance of the fishery, if you will. And we allow for an adjustment to that, which is the Q, which knocks that down if we have changes in flow which make the river less compatible with fisheries production. So the effect then is that poorer flow conditions from a fisheries conservation point of view lead to lower egg to spawner survival and therefore a smaller fishery. And it's measuring the impact of that that gives us the value of lost fishery benefits when we alter the flow to favor, for example, hydropower. And there's other relationships in there. We won't worry about that too much. At the bottom, we have the effort relationship, which it tells us the amount of fishing days that would be incurred to catch the designated amount of fish available to the various fisheries, in particular for the commercial fishery, where Q is the catchability parameter for those who are familiar with that, with fisheries modeling. Okay, I'm going to move on to the different flow scenarios or development scenarios, as we've called them. The first one is the status quo, which is the current conditions, if you will. Scenario 2 is where we alter flow, generally by reducing it overall to emphasize hydropower production. Therefore, there would be greater production of hydropower, but at the expense of less quality for, in the sense of fisheries production, productivity. Then we have a conservation priority scenario, which decreases the amount of hydro that can be produced and emphasizes more productivity for fisheries. That would entail higher flows. And then the pristine conditions as a reference is scenario 4, and that basically reflects the conditions in the 1800s for which flow information is available prior to the building of dams and hydro and flood control and other management measures taken that had an impact on flow. So 4 scenarios. Now these are hydrographs showing these 4 scenarios. You can see the pristine conditions, natural conditions is the higher curve. All of the other ones represent a decrease from that pristine or natural flow condition. These are like over the course of the year on average. And you can see the conservation priority is the highest of those curves, still far below pristine, but higher than the others, emphasizing hydropower or even the current conditions. And so this information is used to help us model potential impacts of productivity of the salmon fisheries in the Columbia River which are associated with the variations in the flow conditions. Now, the way we do that is to create a habitat quality index, which is derived from those flow conditions. So the habitat quality index essentially measures the deviation in the flow measured on a daily basis from the pristine conditions. So when the habitat quality index along the bottom is equal to 1, we're referring to natural pristine conditions, and the opposite would be true at the other end. You'd have no flow at all, basically at 0. So what this plots is the egg to spawner survival, which can be, data is available from the river, in association with different sets of flow conditions, resulting in different levels of the habitat quality index. And unfortunately, the data is quite dispersed. It's quite narrow between 0.25 and 0.75 on the habitat quality index, which is unfortunate. We'd like to have more dispersion so that we could get a better fit. So this is not ideal data, not an ideal, but the relationship was checked against other data, and it appears to be quite reasonable, and fitting the line here gives us the equation that's shown on the right-hand side here, where S is egg to spawner survival and HQI is the habitat quality index. So we could essentially predict spawner survival from the levels of the habitat quality index. Now, the next step was to establish the habitat quality index for each of our scenarios. You can see that in the first column. Pristine conditions, of course, would set the index at 1.0, but the others, and you can see in different ranked order here, the conservation priority has the highest level of the habitat quality index, 0.72, and the hydropower priority has the lowest at 0.57. And you can see the predicted survival in the second column, which is determined from that fitted line. And this gives us a measure of the productivity of the fishery under these different scenarios. The adjustment is just how much you had to reduce the survival rate at pristine conditions under each of the scenarios. So 0.001309 under pristine conditions minus 0.00036652 will give you 0.00094248 as the predicted survival for the conservation priority scenario. Okay, so this gives us the relationships that we needed. We then move forward with simulating the outcomes under each of the scenarios. And this table shows the outputs from the modeling under each scenario. So under the pristine conditions, the exploitable stock would be just over 4 million fish. And under historical allocations, you can see how much would go to the commercial versus recreational versus tribal fisheries. And the total harvest would be just under 1.2 million fish. And then you can see how that changes under each of the scenarios. The conservation priority gives the highest total harvest at 864,000. And in comparison to the hydropower priority, in the far right-hand column, you can see that is just under 200,000 fewer fish available to the fisheries. And so that would be the measure of lost habitat quality as a result of emphasizing hydropower production in that scenario. Okay, so in dollar terms, the net economic benefits are shown here as deviations from the status quo case, or the current situation, which is a value of 36.4 million per year. You can see that the hydropower priority reduces the value of the fishery by 3.5 million. In the best case, the conservation priority under two different sub scenarios, each with slightly, one with 10, which involves a a 10% improvement in flow and one that involves a 20% improvement in flow. And you can see how that leads to up to 7.5 million in additional benefits for the fishery. Under pristine conditions, the fishery could produce as much as 19.5, almost 20 million more than it does at present. So you can see here the economic impacts of the different flow regimes under each of our scenarios. And also the colored bars represent the different fisheries. The commercial fishery, the most important in the pink, recreational fishery not far behind, and the indigenous fishery much, much lower down. Okay, so final observations. Pacific Northwest basins contain habitats obviously to support large salmon populations that haven't always and may not as much now as in the past, but can generate large economic benefits if managed appropriately. However, these habitats have deteriorated in some cases due to land disturbance, which was the case we looked at with the South Thompson River, and in some cases with alteration in flow regimes, such as we've seen in the Columbia River. And the sum total result is that these alterations in habitat quality can lead to fishery losses in the millions of dollars per year. Relatively minor improvements in some cases could lead to improvements in habitat quality and increases in fishery-related benefits. Now, I'm not accounting for the gains or losses in the value of hydro production. That would have to be part of a larger analysis. This is just the fishery piece of that analysis. But basically, our valuation estimates strengthen the case for protecting these habitats, and in particular because it's easy to not see where the value lies, because the fisheries-related values often lie quite distant from where spawning and rearing takes place, and therefore we need to account for that. And of course, there are other benefits associated with these systems, not just the hydropower we haven't accounted for, but also other ecosystem service values that we haven't accounted for. Okay, I just thank my co-authors. There's quite a few of them, so I didn't want to go through all of the list of names, but on the two studies here, you can see the co-authors. Cedar Morton, in the second case, the Columbia River, was the lead author, as based some of his PhD on this work. If you want to ask him more about that, you can contact him at ESSA Consulting in Vancouver. Here, his email is shown here. He'd be happy to receive your questions. And the full paper citations are shown here in case anybody wants to look these papers up to get more details. Okay, thanks a lot, Roy. I'll stop there. Turn it back to you.
Thank you. Thank you very much, Duncan. That was excellent. We have some time for questions from the audience. So there's nothing yet in the Q&A box, but if you have a question for Duncan, please enter it in the Q&A box. I'll kick off the discussion a little bit myself in the meantime. So thanks very, very much for this wonderful overview. So we didn't actually have any of this in previous presentations in the webinar series. The focus on fish habitat fish, commercial fishing, and in the last presentation you also focused on recreational and the importance of fish also for indigenous communities. I guess this is the tribal component. And I was going to ask you a question about the second case study, the trade-off between the hydropower versus the fish revenues. Pristine, I assume, means dam removal. You remove the dams, and so there will be losses of hydropower. So my question, you actually answered it already a little bit, that if you would do a more comprehensive examination, you would also include those. Did you do that? Is there a bit of do you have a bit of an idea of what the revenue lost would be if there would be dam removal? Assuming that it is mainly for hydropower.
Yeah, absolutely. I mean, remember, these pristine conditions are based on flow observations from, I think, the 1870s and 1880s. So It's a bit of a stretch, I suppose, to say that if we removed all the dams, that you would restore the exact flow conditions of the 18th century. Climate has changed, everything else, but there is dam removal, as you may be aware. There has been dam removal, not on the main stem of the Columbia, but certainly in the tributaries. There have been some dams removed, so there is some elements of that happening, benefiting fish populations, obviously, and reversing the losses that are showing up in this modeling.
Mm-hmm. Okay. We have a question actually from Rob Smith, a previous presenter himself. So he thanks you for your interesting discussions. And his question is, when you say your valuations are consistent with welfare valuations, can you clarify what you mean?
Yeah. I work with a lot of fisheries biologists, and they sometimes like to dabble on the economic side, just like we economists like to dabble on the biological side sometimes. And they'll typically just look at how many additional fish are available on, as a result of habitat improvements, and they'll just put a dollar price on, $10 a fish from the marketplace or something, and assign that as the benefits from the conservation improvements. What we're doing here is trying to use a correct theoretical measure of benefit, which for those who are familiar, we're talking about economic rent, producer surplus, consumer surplus type of measures, which are more correct in a theoretical sense. Now that, you can debate whether the extra value of that is worthwhile, but I would argue it is.
Yeah, accounting for the incremental efforts, right? That's
What happens is when you make changes in the environmental quality, and if you're trying to optimize the benefits of the system, you have to make adjustments. If the fishery becomes more productive, even in a small way, you probably need to adjust the amount of effort going into the fishery to reset the optimal level of production and to yield the optimal or maximum level of the economic rent. And that's what's going on with this modeling. We're making constant, the model adjusts as you alter the habitat quality to give you a new value for the fishery, which reflects the adjustments necessary when you change the level of environmental quality. You change the conditions in the fishery, so you got to change the economic activity level too.
Yeah. Which is often forgotten, especially by non-economists.
Yeah. Well,
so Rob, and so you then often get an overestimation of the benefit. So Rob is asking a follow-up question. So he's interested. Do you measure consumer surplus?
No, because we're working with salmon, which I would argue is what's called a tradable commodity. It means its price is fixed internationally. And that means you're working with a flat demand curve, which means there's no consumer surplus taken into account. All of the benefit that we're measuring here as economic rent is on the producer side. It's the difference between the revenues that can be generated and the costs that are incurred to catch the fish.
Yeah. Thanks. Thank you. So Shannon Harris has a question. Can your approach also be applied to fish populations that are not commercially harvested but are valued regardless for biodiversity interests? In British Columbia, many water use plants are in or near the review phase, and I was interested if your approach could be applied in some fashion to inform flow requirements.
Yeah, as long as you can. We're working with a commercial fishery where there's prices and costs and everything is quite observable. With the kind of thing she's referring to, you would still need to be able to establish some sort of values. And that's where stated preference methods might come in. How do people value that biodiversity? How do people value changes in that biodiversity? And then connect that to a biological model so you can see what happens when you make these changes in the habitat in terms of translating into changes in the values people place on the biodiversity. If you improve it, people would value that, and you should be able to extract that. But you'd have to model the economic side of that differently because you're not dealing with commercial values.
Yeah, thank you. I don't see any more questions in the Q&A. Maybe one very last question then from my side. So in the first case study, I was wondering a little bit why the rent was changing so much when you went from scenarios A and B to C and D. So when you started to also modify the habitat qualities of the wider basin. So South Thompson itself doesn't seem to have a lot of effect on the rest of the basin, but vice versa it has.
Yeah, well, I mean, this is the power of the sort of marginality of this. The South Thompson, we're only looking at 16 streams in the South Thompson, is a small proportion of the overall Strait of Georgia basin. Absolutely. And what happens in the rest of the basin has a huge impact on the commercial benefits in the fishery, because it largely determines how many fish are available and how much rent can be obtained from fishing. And the Thompson kind of hitchhikes along with that situation. If you looked at the numbers there, under the first two scenarios, there's about 1 million fish recruited every year at that sort of pristine level of habitat quality in the rest of the basin, the vast area. In the C and D scenarios, that recruitment's reduced to about half that. So there's only about half as many fish in the system, which means it's harder to catch them. It's less profitable to catch them. There's less rent generated, and that's shared by the streams in the South Thompson as well.
Mm-hmm. Yep. Okay. Thanks. Thank you for that clarification. So I think we've approached the end of the webinar. Duncan, thank you so much once again for your amazing presentation, and also for taking the time to answer the question of those who participated today. Those that participated today, thank you so much also for being online with us in this webinar. And I hope to see you again in a month's time. So on May 17th at the same time, we'll have Pascal Badiou, a research scientist from Ducks Unlimited Canada, give a presentation about the valuation of wetlands in agricultural landscapes in Canada. So I hope to see you all again on the 17th of May. Thank you all for participating. Looking forward to see you again in May. Thank you all. And Duncan, thanks once again for taking the time.
Thanks very much for having me. Thank you.
You're very welcome. Thank you. Bye, everyone.